All right, let's dive into a question that sounds like it's been pulled straight out of a sci-fi movie, but is actually tangled up in some of the most fundamental laws of our universe.
So here's the big idea. What if we had enough computing power, I mean a truly staggering amount, could we build a perfect simulation of a piece of our world, starting from its most fundamental building blocks? You know, it seems like it should just be an engineering problem, right? Just build a big enough computer and you're good to go. Well, as we're about to see, it's not quite that simple.
Okay, let's not get crazy here. We won't try to simulate the whole universe or even a person. We're going to start small. With this, just 1 cubic centimeter of a simple crystal. It's tiny, it's orderly. We're going to try and build a perfect digital copy of it, quark by quark. I mean, what could possibly go wrong?
And boom, right away we hit our first massive hurdle. To simulate this thing, we first have to know what we're simulating. So let's zoom in and just start counting the players in our little game.
First up, atoms. In our tiny 1 centimeter cube, we're talking about roughly 700 sextillion atoms. That's a 7 with, get this, 23 zeros after it. That's a number so big it's almost meaningless. But for a perfect simulation, we have to go deeper.
Right, so inside each of those atoms, you've got a nucleus with protons and neutrons. We can just call them nucleons. And at this level, the numbers just explode. We're now at about 42 octillion nucleons. Our to-do list of things to track is getting terrifyingly long, but we're still not at the bottom floor.
Let's get down to the truly fundamental level. Each of those nucleons is made up of 3 quarks. And that brings our grand total to over 126 octillion individual particles that we have to perfectly track. Let me say that again. 126 million billion quarks. And that's just our starting lineup.
So we've got our list of particles, an absolutely insane list, but hey, it's a list. Now all we need is the computer to crunch the numbers. And this, my friends, is where we run face first into what I'm calling the computational wall.
The best tool we've got for a job like this is something called lattice quantum chromodynamics, or lattice QCD for short. The basic idea is you map out the space inside our crystal onto this giant 3D grid, and then you calculate all the particle interactions at every single point. But for it to be accurate, that grid spacing has to be unbelievably tiny, about 1 femtometer, which is roughly the size of a single proton. So you ask, how many grid points do we need for our little 1 centimeter cube? 1 decillion. That is a 1 followed by 39 zeros. At every single one of those points, we need to calculate the state of every single one of our quarks. The scale of this task is it's beyond breathtaking.
And remember, that's just to map out a single snapshot in time. What happens when we actually try to run the simulation, to move forward just one tiny moment in time, one single tick of our simulation clock? What does that cost computationally?
The answer, and you might want to sit down for this, is around 10 to the power of 42 floating point operations, or flops. That's just a basic way we measure computer performance. We are literally running out of names for numbers this big. And let's be crystal clear, this is for one step. A real-time simulation would need billions of these steps every single second. And this just brilliantly shows how hopeless this is. The world's fastest supercomputer can crank out about 10 to the 18 flops per second. Our simulation needs 10 to the 42 flops for a single step. That means you would need a trillion of the world's most powerful computers all working together just to calculate one single fleeting moment in our tiny crystal's life.
So you see, this is the crucial point. We have gone way past an engineering challenge here. This isn't about waiting for our computers to get better. Nope, we are now slamming right up against the fundamental laws of the universe itself.
Let me introduce you to the Bekenstein bound. This is a real law of physics, and it sets a hard, non-negotiable limit on information density. You can think of it like the universe's maximum hard drive capacity. It's a physical law that says you simply cannot cram more information into a given space than this limit allows, or the whole thing will collapse into a black hole.
And here it is, the absolute punchline. The amount of information we would need to perfectly describe the quantum state of all of those quarks is larger than the Bekenstein bound for that 1 centimeter cube. Just let that sink in for a second. The data file for our simulation is physically too big to be stored inside the very object we are trying to simulate. The map is bigger than the territory. And it doesn't stop there. There are other physical walls. The math of quantum mechanics means the info required just explodes exponentially with each new particle you add.
And another law, the Margos-Levitin limit, tells us that to run this simulation would require more energy than the power output of 400,000 suns combined. So yeah, it's not just impossible in practice, it's impossible in principle.
So if a perfect simulation is completely, fundamentally, totally impossible, how on earth does science get anything done? How do we design new materials or discover new drugs? Well, this is where the real genius of science comes in. It is not about brute force. It's about being clever.
See, science succeeds because it doesn't even try to do the impossible. Instead of simulating every last quirk, scientists use these elegant approximations called effective theories, or you might hear it called a multi-scale modeling. It's really all about using the right tool for the right job at the right scale.
So here's how this multi-scale modeling works in practice. At the tiniest, most fundamental level, you use super complex theories for quarks. Then you zoom out and you use different, simpler theories for the electrons. Zoom out again, and you can just model whole atoms as little balls bouncing around. And finally, at the largest scale, you can just treat the crystal as a single continuous object. Each layer cleverly captures the essential behavior of the layer below it without needing all that impossible detail.
And that right there, that's the key takeaway. The goal of science isn't to create a perfect one-to-one digital copy of reality. That's a fool's errand. The goal is to build useful models that accurately predict how things will behave. It's the difference between trying to recreate a forest, leaf by leaf, and just having a map that tells you how to get through it.
So a perfect simulation is impossible, not because our computers are too weak, but because the very laws of physics themselves forbid it. And that forces us to be smarter, to be more creative. Which leaves me with a final thought. What other problems that seem impossible today won't be solved by just throwing more power at them, but by finding a more elegant and clever way of looking at them? Something to think about. Thanks for watching.